We don't rely on climate models to tell us any of that. As I already said, the fact that humans are changing the planet is very basic physics and chemistry, and we don't even need a climate model to tell us that. What we do use these models to do is to try to incorporate some of what we call feedbacks, amplifying factors in the climate system that can actually exacerbate the warming. For example, the melting of ice. When we melt away ice from warming, the planet absorbs more of the incoming solar radiation. It's what we call a positive feedback. It's an amplifying factor. And so the models allow us to incorporate the various feedback mechanisms. They also allow us to make projections of how we might expect rainfall and drought patterns and ocean circulation patterns to change as we continue to warm the planet and change our climate. Now, some critics will tell you that these models are untrustworthy, that they haven't been validated. And mind you, that the atmospheric component of these models is essentially the same physics that we've been using to predict weather for decades. And so these models embrace our physical understanding of the way the atmosphere works, but also the way other components of the climate system, like the oceans and the ice sheets, work, and the way that they all interact with each other, and the effect of changing composition of the Earth's atmosphere in the distribution of heat and radiation. And so these models are simply our best attempt to formalize the physics and the chemistry and even the biology that we know governs the system. But the critics will say, well, the models haven't been validated. They haven't been tested. We shouldn't believe them. And that's simply not true. Okay? And perhaps the most impressive example of a very successful prediction, you might wonder, why am I showing you the restaurant from the Seinfeld show here? Well, in the upper floors of this building, in the Upper West Side of Manhattan, 3 years before the Seinfeld show actually went on the air, Dr. James Hansen of the NASA Goddard Institute for Space Studies was up here in the upper floors of this building running a climate model that by today's standards was actually quite primitive. And as the physicist Niels Bohr once famously said, predictions are hard, especially about the future. And Hansen made a prediction about the future back in 1988. What I'm showing you here is what sort of that 40 years or so of, let's see, this was 1958, 30 years of the instrumental surface temperature record, showing the warming that had been seen over the past few decades in 1988 when Hansen did a simulation. And here are 3 different climate models that he ran. It's a climate model. He did 3 different experiments with that model, where he started out the model with slightly different initial conditions, and so the random internal variations of the climate system were not identical from one simulation to the next, but they all more or less captured the overall warming that had been seen over those few decades. And what Hansen then said was, well, let's look at 3 different possible scenarios for the future. High scenario, where we accelerate in our burning of fossil fuels, a medium scenario, and a low scenario, where we curtail fossil fuel burning fairly rapidly. After all, we controlled our own destiny to some extent through what pathways, what fossil fuel emissions pathways we chose to pursue. And so those are what the 3 simulations looked like. And it turns out that we pursued an emissions pathway that corresponds most closely to scenario B. So let's take the other 2 away. That was essentially what Hansen's prediction was for the pathway that we actually pursued. And that's what actually happened over the next 2 decades. I would argue a pretty successful prediction of the future. Now, if you're a critic, you might point to, you might see the glass as half empty here, and you might say, well, why is it that the model wasn't able to predict this dramatic cooling in 1991, 1992, 1993, nearly a half a degree Celsius, almost a degree Fahrenheit, a huge effect. How could these models be any good if they weren't able to predict something that big, that obvious? And it is true. It is fair to criticize Hansen for not knowing that in 1991 Mount Pinatubo would erupt and put large amounts of sulfate aerosol into the stratosphere, where it would block out some of the incoming sunlight and cool the climate for several years. But what Hansen was able to do, or what he did know, was that it was going to take about 6 months for that aerosol cloud to spread around. So he actually had 6 months to run his model again and predict the amount of cooling that we should see over the next few years from this volcanic eruption. And it turns out that he predicted more or less what was seen, a cooling of about half a degree for a few years. So it was actually not a problem with the climate model, it was another successful validation of the climate model. All right, well, so I've talked about volcanic eruptions and they can cool the climate. So that's an example of a natural factor that can influence the climate. And there are measurable, small, if small, but measurable changes in the output of the sun and the brightness of the sun over time that have an influence on the climate. And so there are these natural factors that could come into play. And if you're a critic, you might say, well, okay, Hansen was able to explain the warming with greenhouse gases, but maybe that's not it. Maybe it's these natural factors that are responsible for the warming that we've seen. Well, we can use the models to actually test that hypothesis. We can put the volcanoes in there, we can put the measurable changes in solar output in the models and see what they predict. And that's what you get, okay? So in fact, not only can natural factors not explain the warming of the past several decades, the climate should have cooled if natural factors were primarily at work. All right, well, what happens when we put in the human factors? Increasing greenhouse gases from fossil fuel burning and other activities, but also a secondary impact of our own production of aerosols, not volcanic aerosols that are natural, but pollution from smokestacks, what are known as sulfate and nitrate aerosols that are produced by industrial activity that also have a short-term cooling influence, but as long as they're produced constantly, they have a cooling impact in certain regions of the globe. And so that actually offset global warming for several decades until let me show what the simulations actually say. So warming was actually held back for several decades by these pollutants, by these aerosols that had a cooling influence on industrial regions and regions downstream from them. But then we smartly, because we were acidifying our lakes and we were destroying structures, human-made structures, we were destroying our environment through acid rain. We passed the Clean Air Acts in the US and the UK and other countries to scrub those sulfate aerosols out of the smokestacks before they made it up into the atmosphere. And when we did that, we unmasked all of that warming that had been hidden for decades by this pollution effect. And that's why we've seen the acceleration of warming in recent decades. We've seen the full brunt of the greenhouse warming. It would be unwise to say, well, maybe we should go back to putting sulfate aerosols into the atmosphere and acidifying our lakes because it would help out the climate change problem. That would certainly be a Faustian bargain if there ever was one. So, what about the future? Okay, so we've seen the models, have made successful predictions.